Hey everybody, Dr. A here, and in this video we're going to be exploring another example of applying virtual work to analyze a truss. So let's go ahead and get started. In the given information, we're being asked to determine the vertical force P required to prevent joint A from displacing vertically. And we're also being told that member AC is subject to a 90-degree temperature increase. So here we have a 3-bar truss. We have member AB and BC each having 4 feet of length. There's an external hinge at B and a vertical surface roller at C. Now notice that there's no applied loads anywhere here at this point, right? It's just a truss hanging out there, no applied loads. And what we're being asked to find is a vertical force P that we can put at A that will prevent joint A from displacing. So how is joint A going to displace if there's no applied load right now? Well, joint A is going to displace because right now member AC is subjected to a 90-degree temperature increase. So there's some kind of heat source here that's radiating heat that's heating up member AC by 90 degrees. And that's going to cause joint A to move somewhere, okay? And so if we want to negate or neutralize a vertical displacement of point A, then we need to put a load there. We need to somehow impose a load at joint A, and that load is what we're trying to find. So we're also being told that all 3 members have a cross-section area of 5 square inches. They all are made of the same material, which this happens to be steel. 29,000 kips per square inch is the modulus elasticity. And they all have a coefficient of thermal expansion of 6.5 times 10 to the negative 6, 1 over degrees Fahrenheit, okay? So that's the situation we have. So I'm going to start by writing solution here, and I'm going to say we need to note that A will displace due to that change in temperature being 90 degrees Fahrenheit. And we're trying to find that load, a load P that we can put at A to prevent a vertical displacement, okay? So how are we going to go about doing this? Well, the first thing we need to keep in our back pocket is that we're going to end up using the overarching large virtual work formula, okay? And so we're going to keep that in our back pocket for a later step. Now, just like we've seen in previous examples, we can consolidate steps 1 through 3 by drawing the virtual truss and analyzing it. So I'm going to say analyze the virtual truss using method of joints, okay? So how do I do that? Well, I'm going to sketch this virtual truss here. Remember, it's got the same geometry as the real truss. So it's going to have this pin here, this roller here, except I'm going to put a virtual load of 1 kip at joint A, all right? And of course, this is, 4 feet and 4 feet, and of course, this will be 45 degrees and 45 degrees, all right? So we're going to use method of joints first, and I'm going to come over here and I'm going to do that kind of quickly now. I'm going to say let's look at a free body diagram of joint A first. So by now we should be experts at method of joints. This is little f AB. This is little f AC, 45 degrees here. And so we can say sum of the forces in the y direction equals 0, negative 1 kip minus little f AC times the sine of 45 degrees equals 0. Little f AC comes out to be a negative 1.414 kips we're going to say sum of the forces in the x direction equals 0, and we're going to have little f AB minus 1.414 kips times the cosine of 45 degrees equals 0, and we'll get little f AB is equal to 1 kip. That'll be positive. And then I'm going to move on to a free body diagram of joint C. And so I'm going to have FBC here. So we can draw that here, little FBC. And then I've got little FAC, which I already figured out is 1.414 kips in compression. And you know we have all these 45-degree angles. And so we can say sum of the forces in the y direction equals 0. And we can quickly determine that FBC is also 1 kip, okay? And that'll also be positive, so that's going to be in tension, all right? So what do I do now? Well, I have my little f forces, okay? Now I'm going to use the scaling technique. Now watch this. I'm going to say scale the little f forces by P, okay? And so when I do that, I'm going to get the following. I'm going to get capital F AC is going to be negative 1.414 P, and that's going to carry units of kips, of course. And then I'm going to get capital F AB is P, and capital F BC is also just P, okay? And again, carrying units of kips. Now what I'm going to do is I'm going to set up my table, my help table that I use to help me evaluate this, and I'm going to apply the virtual work formula. But like we said this time, we've got temperature and we're trying to find a particular force. So we're going to have temperature and the force term all together. So what my virtual work formula is going to look like is 1 kip times delta vertical A equals the sum as I goes from 1 to 3 of FFL over AE sub I plus the sum as I goes from 1 to 3 of alpha delta TL sub I. Now, our direction said that we want 0 vertical deflection, so we're going to say this collectively is going to be 0. So we want, when we add these two terms up, to give us a net 0 vertical displacement, okay? Now, what does this kind of sort of remind us of? This is very similar to applying what's called a compatibility equation if we were to analyze a statically indeterminate system. That's not what we're doing here, but mathematically it's very similar to what we have learned in maybe like a mechanics of materials setting where we got introduced to statically indeterminate systems and we needed an extra equation called a compatibility equation. So this is quite similar to that concept, okay? So just keep that in your back pocket for maybe another video when we explore indeterminate systems, okay? So from here, I'm going to set up my table like we do pretty much all the time for these kinds of problems. Okay, so I'm going to have my member or member list. And then I'm going to have the length of each member, and I'm going to go ahead and put those in inches. So you want to convert those feet to inches for the lengths. And then we're going to have our little forces in kips. And then we've got our capital forces also, which will collectively have units of kips. And then I've got delta T in degrees Fahrenheit. And then I'm going to have my F, let's write them in the order we're used to. FL over AE. And we're going to explore those units here in a minute. I like exploring the units kind of sometimes after we do the calculations. And then I'm going to have my F alpha delta T L. Okay, so let's say we've got member AB, AC, and BC, and those lengths are 48 inches, 67.88 inches, and 48 inches. Again, I converted those lengths that were in feet into inches. I've got 1 for little FAB, and then negative 1.414 for little FAC, and then 1 for little FBC. Now the capital F forces, that's where I've got P, negative 1.414 P, and then P again. And then the changes in temperature, only AC had a change in temperature of 90 degrees. So AB and BC temp changes are both 0, okay? Now what I'm going to do is I'm going to start multiplying things together. FFL over AE. Now, remember, do we know A and E? Yeah. If you don't remember them, we can sketch them over here. If you remember from the problem statement, A had unit was values of 5 square inches, and E was 29,000 KSI for all the members. Okay, so all 3 members had the same A and E values. All right, so let's track our units here. I'm going to have F and F, which is going to give me kips times kips, so kips squared, times inches, divided by AE, okay? So what is that going to come out to be when I piece all that together in terms of units? Well, I should end up getting units of kips times inches of some sort, or really like, you know, P times inches. So I'm going to put a little dash and say times inches. Now, the reason why I'm putting a dash here, even though it seems like it should be kips times inches, is because right now, yes, the capital F forces have units of kips, but right now they're just in terms of P right now. So P is in and of itself, it's self-contained. It's got units built into it. So I'm not going to write those in for the capital F forces, but you know, you could work out the units a little bit and see that, you know, you're going to have like units of P times inches. Okay, so let's go ahead and crank these through. When maybe pause the video and see if you can get the same things I'm getting, but I get the following when I crank these through. I get 0.000331 for member AB, and that's going to be times P. Okay, remember, capital F is P, so that P is hanging out there. Okay, next I've got 0.000936 times P, and then for BC, I've got 0.000331 P again. Okay, so pause the video and make sure you're getting these same values. Okay, what about the temperature or the thermal term? I've got little f times alpha times delta T times L. Do I know alpha? Yeah, we also said alpha is 6.5 times 10 to the negative sixth 1 over degrees Fahrenheit for all the members. So when I crank all of these through, I'll quickly figure out 2 of these are 0 because 2 of these members had a change in temperature of 0. So that's pretty straightforward. Pause the video, see if you get the same thing as me on this AC member, but I get negative 0.0561. Now, what are the units here? Well, these should be kip times inches here, okay? Kips times inches. And again, that makes sense. Little f has units of kips. The alpha and the delta T temperature units cancel, and then L has units of inches. So when I piece all of this together, what do I get? Well, I can sum these columns down, all right, just like I've done before. And for this sum here, what do I get? Let's do it together. 0.000331. Double that because there's 2 of them. Add that to 0.000936. And so here I get 0.001598. And then this one, of course, this sum over here is negative 0.0561. And again, we're being mindful of our units here. Now, what do I need to make sure I don't forget? This still has P hanging out in front of it, right? We still have 0.001598 P, okay? So now I'm going to enter these in to this equation here. So the 0.001598 P, which term is that? That's this entire term, okay? And then the negative 0.0561 kip inches, this is this entire term. So now I can write 0.001598, and this is going to have units, of inches times P equals negative 0.0561 kips times inches, and then I can do some rearranging, and let's see what we get. 0.0561 divide over, I get P equals 35.1 kips, and actually this should be correct one thing. This should be a positive here. Why is that positive? Well, remember, you say this term plus this term equals 0, and so in my work I just went ahead and I moved this over to the right side of the equation, so the negative went to the right side, became positive. Okay, so this becomes a P equals positive 35.1, and that means it's pointing in the direction that we assumed our virtual load to be in. And so this is our final answer. So hopefully you found this example helpful to you. This is more of a challenging example. If you found this helpful for you, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.